We have all been there where we are sitting on the edge of our seat and watching a very crucial moment of a match, or we are watching a climax scene of a movie, and all of a sudden the video pauses, the audio cuts out, and all you see is an annoying spinning icon in the middle of the screen. Hello everyone, my name is Nikunj Padia, and today I'm going to talk about the science of streaming. In this presentation, I'm going to unpack why that happens and what the engineers do to behind the scene to avoid this. I'll be focusing on the quality of experience in HTTP adaptive streaming, which is the technology behind services like Netflix and YouTube. And hopefully, by the end of this, you'll see that streaming is not a magic. Rather, it is a series of careful trade offs designed to protect the user experience. Now, to understand the quality of experience, we have to start with the basic mismatch between the internet and video playback. The thing is that network is not a nice steady pipe. The bandwidth goes up and down all the time. On the other hand, the video playback wants a smooth continuous flow of bytes. If the network throughput falls below the video's bitrate for a long enough time, then the player simply runs out of data and has to pause. This is where we distinguish the quality of service from quality of experience. The quality of service is what the network is doing. The quality of experience is what the user actually feels. Things like, did the video start quickly? Did it stall? Was the picture too sharp or blocky? And in Seufert survey, the quality of experience is measured using the user studies and subjective ratings tied to these impartments. The core challenge of streaming is to make messy, fluctuating quality of service and turn it into a consistently high quality of experience. The main tool that makes this possible is HTTP adaptive streaming. What server does is that instead of sending a giant video file to the client, it chops the file down into multiple segments, and each segment is of around 2 to 10 seconds. And after chopping those files down into multiple segments, it stores each and every segment at different quality or at different resolutions. So for example, as we can see in the diagram, segment 1 has been stored at different resolutions: 1080p, 720p, 360p, 240p, and so on and so forth. Now, in HTTP adaptive streaming, the client is in charge. So at the client end, the video player runs adaptive bitrate algorithm. For every upcoming segments, that algorithm measures things like what was the recent throughput, how full the buffer is, and then it chooses which representation of the video should it ask the server for. So if the network is looking good, it will ask for a higher quality chunk, and if the network is not looking that good, it will ask for a lower quality chunk. So HTTP adaptive streaming turns streaming into a repetitive decision problem where every few seconds the player asks, given the current condition, what quality should I pick to make the user happy? Seufert took a large body of quality of experience experiments and organized them around what actually annoys the user the most. And 3 factors stood out as enemy of the video experience. The first was initial delay, that is how long you'll have to wait before video starts playing. Interestingly, the survey observes that users are relatively tolerant here. The short delay in the startups of a couple of seconds is annoying, but it's not catastrophic, especially if the rest of the playback is smooth. The second factor was quality switching. This happens when the picture quality jumps between sharp and blurry as the player changes the bitrate. Users notice these changes and they don't love them, but they are somewhat acceptable if the video keeps on playing. The third and the worst is stalling or rebuffering, when the video playback freezes and that little annoying spinner appears. And that's where the user subjective rating drops sharply. Even a short stall can dominate the quality of experience score. Many experiments in the survey show that people would rather watch a low resolution video but a smooth stream than watching a high resolution video with stalls. And these are the three factors which act as foundation of the design rules we will see next. Putting those findings together, we have what we call the golden trade-off for adaptive streaming. As we have noticed that stalling is damaging to the quality of experience, but quality switches are somewhat tolerable, and hence the streaming systems are designed such that they will sacrifice the resolution long before they allow the buffering to run empty. In other words, the system will choose slightly ugly but smooth over beautiful but frozen. We can think of quality of experience as a function of three variables: average quality, number and duration of the stalls, and lastly, the amount of quality switching. And experiment results from Seufert and related work shows that the slope of quality of experience with respect to stalling is much more steeper than with respect to the quality. A single stall can undo the benefits of a big jump in resolution. So in almost all practical situations, it's better to drop one from 1080p to say 480p or even 360p if required than to risk the rebuffering event. Modern players encode this logic directly into their adaptive strategies. Now let's look at how the player actually implements the trade-off in real time. You can think of adaptive streaming as a feedback control loop running every few seconds. First, the player measures current conditions. It estimates the recent download throughput and checks how many seconds of video are currently buffered. And based on those measurements, the player's algorithm chooses a bit rate for the next segment. Say if the buffer is high and the downloads are happening fast, then it can safely request for a higher quality chunk from the server. But if the buffer is shrinking or throughputs are looking a bit shaky, it will switch down to a lower quality bit rate to refill the buffer quickly. Then after each downloads, the buffer level is updated, and then player goes back to the beginning of loop and starts everything again for the next segment. So far, I have described HTTP adaptive streaming in abstract terms, but real systems use concrete streaming formats, and two big ones are HLS and MPEG-Dash. So HLS, which stands for HTTP Live Streaming, was developed by Apple and is deeply integrated into iOS and macOS ecosystems. So if you are streaming on an iPhone, there is a very good chance that it is using HLS under the hood. Whereas MPEG-Dash is an open international standard that emerged from rest of the industry. It generalizes the same ideas of segment-based HTTP delivered videos with manifest files, but the only difference is that it isn't tied to a specific vendor. For the longest of times, the content providers had to store two versions of each piece of content, one packed in HLS and another one packed for MPEG-Dash, which was obviously a huge waste of space and infrastructure. And that's where CMAF, which stands for Common Media Application Format, comes in. It defines a unified container that both HLS and MPEG-Dash can use. In practice, this lets provider keep a single set of encoded segments and use those across the ecosystems, reducing the storage overhead and simplifying global content delivery. Next, let's zoom back into that player and talk about how it decides what bitrate to pick. So a naive approach is purely throughput based, that is, measure the last download rate multiplied by a safety factor and pick the highest bitrate that fits. The problem is that throughput is very noisy, and wireless networks in particular can fluctuate rapidly, and if the algorithm chases the fluctuation, you'll constantly get quality switches and even sometimes unexpected stalls. The BOLA, which is the buffer occupancy based Lyapunov algorithm, is a major step forward. In this algorithm, instead of predicting the bandwidth precisely, it looks primarily at buffer level. It defines a utility function that rewards higher quality but it penalizes lower buffer. So for every candidate bitrate, it estimates how that choice will change buffer and pick the option that maximizes the utility. This buffer based view naturally smoothens the short term noise in throughput. BOLA tends to keep buffer in safe region, which reduce both stalling and unnecessary oscillation in quality. This is the reason why variants of BOLA or BOLA like algorithms are widely used in modern dash players. So far, everything that we have discussed today is under an assumption that underlying transportation protocol is TCP, and that is the case for most of the video streaming today. But there is a key limitation in TCP, and that is of head of line blocking. That is, in TCP, all data on a connection is delivered as one ordered byte stream. That is, if a packet is lost, the receiver must wait for the packet to be retransmitted before it can deliver any later bytes to the application. That means that a single packet lost can delay an entire set of the video segments, even if the most of its data has arrived on time. Whereas QUIC, which underpins HTTP3, takes a different approach. It runs over UDP and implements its own reliability and congestion control. But crucially, it supports multiple independent streams within a single connection. So, loss on one stream does not block the delivery on others in the same way. So, for streaming, this reduces the head of line blocking at application and cuts the connection setup overhead. This would help us lower both startup delays and risk of rebuffering, especially on a lousy network. QUIC is therefore a key enabler for low latency live streaming and more resilient video delivery. To summarize, streaming is all about turning messy network behaviors into good quality of experience. The Surfeit survey shows that stalling is the single most damaging compartment, followed by quality switches and then delayed startups. The HTTP adaptive streaming addresses this problem by segmenting the video down and storing multiple qualities of that segment and letting the client side's algorithm decide which quality to fetch for the next segment. Standards like HLS, Dash, CMF makes this idea deployable at internet scale, while the smarter algorithms like BOLA and transport innovations like QUIC further reduces the stall and unnecessary quality changes. The end goal of all this engineering is simple: keep the movie going and keep the loading sphere out of sight. Thank you so much, everyone.